We have an ambitious plan for today. We're going to briefly review the discriminant functions. We're going to discuss why the sigmoid function is the right choice for binary classifications. We're going to find the new decision boundary. We're going to prove that the new cost function is convex, and we're going to derive the new gradient descent algorithm. Let's look at an example when we're trying to classify whether an email is spam or not spam, and the feature we're going to look at is the number of words in the email that are entirely capitalized. So we have a single feature, which is the number of words entirely capitalized in the email. And let's say that our discriminant function has already been trained so that we already have a bias term, -4, and the coefficient for our feature is 1, as you can see in the vector to the far right. Later on, we're going to see how to find and train these coefficients, but for now, let's just assume that it's already been trained. Some people like to put the bias term separately. I like to integrate it into the vector. So our discriminant function for our feature, our single feature, is x minus 4. If the discriminant function is positive for some email, then that's a spam email. If it is negative, then the email is not spam. So the set containing all of the feature values that would classify this as spam is 5 words that are entirely capitalized, or 6, or 7, or 8, or indeed anything greater or equal to 5 will be classified as spam for this single feature. And if the email only has 0, 1, 2, or 3, in this case, then it's going to be classified as good. Our boundary plane is x equal to 4. What does that mean? That if an email has exactly 4 words that are entirely capitalized, then the discriminant function is identically equal to 0, and this is the boundary between where we decide a spam email or a good email. So let's look at a more complex example. Let's say that the emails do not just have one feature. Let's say they have 3 features. We're going to count all of the words that are entirely capitalized in the email. We're also going to count the number of exclamation points that are together. And we're also going to count the number of times that a number replaces a letter in the word. So for example, let's say that we have an email that has 3 exclamation points together. It has 3 words that are entirely capitalized, and in 3 instances the words have letters that have been replaced by numbers. This is clearly a spam email. When we apply the discriminant function that has been pre-trained to this email, we get a positive number. So that means that this email is indeed spam. On the other hand, let's consider another example. Let's say that there's an email that only has 1 exclamation point. It only has 1 word that is entirely capitalized, and in no case does a word in this email have a letter replaced by a number. When we apply the pre-trained discriminant function in this case, then we're going to get is a negative number. This is not spam. Anytime that an email comes in whose features, when you apply the discriminant function, give you a positive number, it's going to be labeled spam. Anytime an email comes in whose features, when you apply the discriminant function, is a negative number, then this is not spam. So we now know that the feature space is divided into the segment R1, where all the features of the emails are going to give you a positive number and therefore are spam, and are not, that's the lower left side, where all of the emails that have features that give you a negative evaluation of the discriminant function, those are not spam. Those are good emails. The 2 areas are separated from each other by the boundary plane. And the boundary plane has the characteristic that any email whose feature vector falls on this boundary plane, when you apply the discriminant function, that's going to be equal to 0. Let's compare how we're going to train our models with linear regression and logistic regression. In linear regression, every instance, even outlier features, are equally used in training the model. Let's say, for example, that you're trying to do a machine learning algorithm that estimates the length of a newborn baby with respect to its weight. In this case, every newborn that is born in the hospital is taken into account in our model. Even very tall babies or very short babies are going to be affecting our model. On the other hand, when you look at logistic regression, some instances shouldn't really affect our model for a good design. Let's go back to the fact that we're trying to determine whether an email is spam or it's not spam. If an email, for example, has all of its words entirely capitalized, and all the words also have numbers that replace letters in them, and let's say that every sentence is followed by 4 exclamation points in a row or more, this is a slam dunk case of spam, isn't it? These instances shouldn't really affect the model. Why? Because slam dunk cases are easy to classify whether they are spam or not. The quality of our machine learning algorithm is really going to be determined by how well does our machine learning algorithm detect spam in the near the boundary plane. In other words, when something is questionably spam or not spam, how good of a job does it do it? Our model should be trained to estimate near the decision boundary. That should be the area where we spend most of our efforts to make a good design. The slam dunk cases really aren't a problem. They should do a good job anyway, just because their numbers should be very far from the decision boundary. This is where we see the value of the sigmoid function. You can see the formula for the sigmoid function right there, 1 over 1 plus e to the minus argument. In this case, the argument is going to be g of x vector, and it's going to be a scalar value. Now, the properties of the sigmoid function is that the domain goes from minus infinity to infinity. Its range, in other words, the output, is anywhere from 0, that's the asymptote on the left side, to 1, the asymptote on the right side. At the origin, the sigmoid function evaluates to 1/2, the midpoint. It has the advantage that it is monotonically increasing. And remember, we talked about this. This is really good for discriminant functions. It's a useful property. In addition to that, the sigmoid function is continuous and smooth and differentiable everywhere. Again, we talked about this before. These are all good for discriminant functions. The nice thing about the sigmoid function is that it zooms in on values in the transition region. In other words, the area near the boundary, roughly between -6 to +6. At -6, the value of the sigmoid function is about 2.5 times 10 to the negative 3. And at value 6, it's 1 minus 2.5 times 10 to the negative 3. You don't really need to focus beyond that, because when you go beyond those regions, you go into the slam dunk regions. What you do need to focus on is near the decision boundary, because that's the area where your machine learning algorithm is going to be evaluated, whether it's an effective one or a non-effective one. So what are the questions we're going to address today? How do we define our new discriminant function now that we're using the sigmoid function? What is the new decision boundary? Does it change now that we're using the sigmoid function? What about the new cost function? Will it still be convex? We're going to prove that it is. And finally, how does the gradient descent going to look like with our new system? So this is what our new discriminant function is going to look like for binary classification. The GNU will be parameterized by W, in other words, the weight vector that we are trying to train, and it is a function of the feature vector of every new instance. As a convention for these slides, every time you see a blue X vector, that means it's the feature vector for our new instance. So it's the number of entirely capitalized words, or the number of exclamation points, or the number of words that have letters replaced by numbers, or things like that. That's going to be blue. The red W is the thing we're trying to train in machine learning. In other words, we want to use example instances to be able to find the optimum W. Now that we're implementing the sigmoid function, then this g nu is going to be the sigmoid function, and its argument is going to be W transpose X. It used to be just W transpose X for linear regression, but now for logistic regression, it's the sigmoid function of W transpose X. And we know that that's 1 over 1 plus e to the minus whatever's in the argument of the sigmoid function. The old decision boundary was set where W transpose X was equal to 0. Well, we're going to do the same thing here. The new discriminant function, which is sigmoid function evaluated at W transpose X, is where the sigma is evaluated at 0. And we know that that's 1 over 1 plus e to the minus 0, which is 1/2. That tells us that our new decision boundary for an email with feature vector X is wherever the g nu of X will be equal to 1/2. In other words, if g nu of X is greater than 1/2, we're going to decide that the email is spam. If the g nu of X is less than 1/2, we're going to decide that it's not spam. Let's talk about the cost function now. Let's say we have a single instance, a single example email J, and its feature vector is going to be the vector X with the J superscript. That indicates that this feature vector is associated to that instance. Its cost function will, of course, depend on the feature vector X, but it will also depend on the trained weight W. We're going to find it as minus natural log of the discriminant function if it's actually a spam example, and it's going to be minus natural log of 1 minus the discriminant function if the email is not spam. In other words, it's a good email. In each case, the label for spam is 1 and the label for not spam is 0. We know that we want the natural log in there since the sigmoid function has an exponential function inside of it, so that's a good thing. We also want to make sure that the cost function is small when our estimate is correct and big when the estimate is wrong. Let's see if our cost function complies with our requirement. Let's give an example that we get an email which is spam. In other words, it should be that the discriminant is actually approximately equal to 0. If the discriminant is approximately equal to 0, in other words, we select not spam, then minus log of the discriminant is going to go towards infinity. On the other hand, if the email is spam and the discriminant is equal to 1 or something approximately equal to 1, then we're going to select yes spam. In that case, the cost is equal to 0. This complies with what we wanted. Let's look at the opposite case. Let's say that we have an instance that is not spam. It's a good email. Well, what is the cost function going to look like in this case? Well, if the discriminant function is equal to 0 or something close to 0, we're going to select not spam. This is the correct decision, and minus log of 1 minus g is going to be equal to 0 or very close to 0, which is exactly what we wanted. On the other hand, if g is approximately equal to 1, that makes us select yes spam. That's the wrong decision. And in this case, minus log of 1 minus g is going to go towards infinity, so it punishes the bad decision. So far we know that this cost function is going to be small when we get the decision correct, and it's going to be big when the estimate is wrong. So it's a really good candidate for a cost function. The only problem that we'd like to fix at this point is the fact that we don't like our cost function to be written as cases. Why? Because when we want to do the gradient descent, the gradient descent means a derivative, and taking a derivative in cases is just not a smooth solution. We'd like to have this cost function written in a single line, which is what we're going to do next. Let's look at our cost function in the two cases, when an email is spam and when an email is not spam. Let's start with the example that an email is spam. In other words, omega 1 is true. The email is spam. In that case, the cost function that we saw before is minus log of g. But we're looking only at the cases where the emails are spam. In other words, we're looking only at the cases where the label is 1. That means that when I look at the cost, which is minus log of g, I could just as easily multiply that by 1. But since for all of these instances the label is equal to 1, I could replace that 1 with the label. Now let's look at the other case. Say that the email is not spam. We're only looking at the instances of good emails that are not spam. In those cases, the cost is minus log of 1 minus g. All right, but since we know that all of these instances are not spam, we know that their labels must be 0. Well, that means that 1 minus the label, 1 minus y, is equal to 1 minus 0, which is equal to 1. That means that I could write the cost function as minus log of 1 minus g, and I could multiply that term by 1. But for all of these examples, that 1 is equal to 1 minus y. So I could just replace it with 1 minus y, confident that in all of these cases, y is going to be equal to 0. Let's put the two guys together. Say that for any given instance, and this time we don't know if the instance is spam or not spam, we write the cost as y times minus log of g plus 1 minus y times minus log of 1 minus g. Well, if it turns out that the specific instance is spam, then y is going to be equal to 1, and 1 minus y is going to be equal to 0. Therefore, in this particular case, what happens is that the right side term disappears. What happens if the particular instance we're looking for is not a spam email? Well, in that case, we know that the label is equal to 0, which means that the left side term gets multiplied by 0 and the right side term gets multiplied by 1. In other words, the left side terms vanishes, and we end up with exactly the correct formula in each of the two possible cases. So now we know that we can write the cost for any single instance. Instead of writing it in 2 lines like we have above, we can write it in 1 line. And the reason we did this is because later on we want to take the derivative in order to do our gradient descent. And having it in 1 line is just a lot more helpful. But of course this cost is only for one example, one instance. For all instances, for all training examples, our average cost is going to be 1 over n, in other words, where n is the total number of examples that we're using for training, and the summation of each of the individual cost functions applied to their individual feature vectors. We already saw in our course that for linear regression, the maximum likelihood result for the optimum weight vector, what's the optimum weight vector? It is the actually trained set of coefficients for our features, was obtained using gradient descent. In other words, the best W we can use to train our machine is that W which minimizes the total cost. What is the total cost? It's the average of the individual costs of all of our training instances. Remember how we talked about approaching W through the gradient descent. How did we do that? Well, we started at an arbitrary initial point. Then we evaluated the gradient of the cost and evaluated it at that point. What was the gradient of the cost again? Well, it's a vector of all the partial derivatives of the total cost with respect to each of the coefficients. Remember that in our course, W0 is the coefficient that multiplies the bias term. It multiplies 1. It doesn't multiply any of the feature vectors. It's simply the offset. All the other W's are coefficients of the features for each individual instance. What are the features? Well, how many words in your email are entirely capitalized? How many words in your email have a letter replaced by a number? And how many expressions in your email have a lot of exclamation points together? Those are the features. And W1, W2, etc. are the coefficients of these features. All of the features in our example of an email, we have 4 features if you include the bias. It would be the bias plus the number of capitalized words plus the number of words with numbers in them and the number of consecutive exclamation points. That's 4. D would be equal to 4 in our example. And at every step, we talked about this in linear regression, at every step you get closer to the optimum W when you take the previous W from the previous step and you subtract eta times the gradient of the cost function evaluated at the previous W. Let's prove how you get this gradient. And let's get some intuition about why this gradient descent works. Let's remind ourselves about what we talked about in gradient descent in linear regression. Let's say you just want to minimize any arbitrary function j with respect to its argument a. Well, if j is convex, then gradient descent tells us that we can start in any arbitrary position. And we ask ourselves, are we going to move to the right? In other words, make a bigger a towards our minimum j? Or alternatively, are we going to move to the left towards the minimum of j? Our choice of the direction we're going to move really depends on the slope of the function j at that point with respect to a. In this case, the derivative is positive. It tells us which direction to move to get to lower ground. In other words, we need to choose a smaller a in order to get to lower ground. And our new selection of a is going to be equal to our old selection minus some amount. And a good question is, well, how big of a step are we going to take in order to, once we choose what direction to move in? If we choose a step size that's really, really small, it will get you to the minimum, but it may take a very large number of computations. In other words, it will not necessarily be an optimal use of your resources if every time you update your A, you take a very tiny step in making the choice of the next A. What happens if I choose a step function that is too big? Well, in that case, I might actually overshoot the minimum of j. That may cause resonance, in which case I will never reach the optimum value of a no matter how many iterations I go. And I will never get any closer to the minimum of j. So what's a good idea for choosing our step size? In a convex function, if you're far away from the minimum, it makes sense to make a big step towards the minimum. That way, when you update your a, the new a will be equal to the previous a minus a big step. If, on the other hand, I'm already very close to the minimum of j, well, it makes sense to take a small step so that the new a is equal to the previous a minus a very small step. So the step size delta is going to be big or small depending on the derivative that you experience at that current a position. That tells us that in gradient descent, our step size should be proportional to the derivative at our current point. And that constant that multiplies the gradient and regulates the step size is called the learning rate, which we're going to denote as eta, which we already talked about in linear regression. So what happens if we have more than one feature for each one of our instances? So instead of just knowing the number of capitalized words, we are also taking into account the number of exclamation points. In that case, our cost will be two-dimensional. Of course, it can be three-dimensional, four-dimensional, five-dimensional, however many dimensions we want. But in this graph, we're seeing a two-dimensional feature vector and the cost function. So we start at an arbitrary position, in this case a equal to 0.4 and b equal to negative 0.35, and we take the partial derivative along each direction. Let's start with the variable a. We take the partial derivative of the cost with respect to a, and it tells us in this case that we have to go towards a smaller a in order to reach the minimum. Now let's look at it from the other variable's perspective, from b. You start from the same arbitrary point, but now you want to look at the slope along the b variable direction. So we take the partial derivative of the cost j with respect to b and see where that slope takes us, towards the right or towards the left. Let's get into the nitty-gritty and continue answering our questions. In this case, what is the gradient? Well, it's the vector of partial derivatives of the cost function with respect to the coefficients. Remember, the red W are the coefficients, the thing that we're looking for. And anything blue has to do with the training instances. The Y means the label, and the X vector is the vector of features. So we're taking the partial derivative of the total cost function with respect to the W vector. Well, remember that this partial derivative is with respect to the red W. So anything that's blue is actually a constant with respect to this derivative. So we can invoke the linearity of derivatives, or the linearity of gradient, to take the partial derivatives inside of the summation. We know that the thing inside of the log is the sigmoid function evaluated at W transpose X. So we can go ahead and replace it there. Now let's look at just the left derivative for a moment. We're going to invoke the chain rule of derivatives to take this partial derivative. We know that it's a partial derivative with respect to W of the log of 1 over 1 plus e to the minus W transpose X. Well, with the chain rule, we know that we first want to take the log prime. Then we want to take the argument of the log prime. Here by prime I mean the derivative of. Then, since the argument is 1 over something, we want to take the denominator prime. So we start with the derivative of the natural log. Whatever that is, it's going to be 1 over whatever's inside the natural log. Then we take the derivative of 1 over something. When we have that, you know that it's going to be, the derivative is going to be equal to minus 1 over that denominator squared. Then, according to the chain rule, we multiply that with the derivative of the denominator. In this case, the denominator is 1 plus e to the something. So the derivative of that is 0, because 1 is a constant, so its derivative is 0, plus e to whatever that stuff is. And finally, the chain rule tells us take the derivative of that exponent of e. With that, we're going to have that partial derivative. I know it looks long and unfriendly, but it's, I promise you, a lot of stuff cancels out. All right, let's continue working on that leftmost term. Well, let's give us some space here. We already found out what we should replace each one of these prime expressions with. The derivative of the log is 1 over the argument. So that's 1 over 1 plus e to the minus W transpose X. Then we had 1 over some stuff. When you take the derivative of that, it's minus 1 over the denominator squared. Then we took the derivative of 1 plus e to the minus w transpose x, in other words, the derivative of the denominator. And finally, we took the derivative of minus w transpose x. Now, from one of the properties that you'll find in our course resources in the PDF file with the linear algebra identities, you'll know that the derivative of w transpose m with respect to w is equal to the derivative of m transpose w with respect to w, which is equal to m. So we know that the derivative of minus w transpose x is going to be minus 1 times x, since x is sort of the m in this example. Well, now we know how to simplify this expression. 1 over something is just that something. So the leftmost term turns into 1 plus e to the minus w transpose x. Next, well, the next term there's not much we can do about now, so we just copy it the same way. 0 plus something is just that something, so we could simplify that. And finally, we get minus x vector. Now, if you'll notice, the leftmost term is actually the same term as which is in the denominator squared, so we could actually cancel those two out. That helps us simplify stuff. The other thing is that there are two minus 1's which also cancel each other out. So we can simplify that one as well. Now that we've found the leftmost derivative and we've found a way to simplify it, we can plug that into our original gradient. Look, let's go ahead and plug that in now. Now we're going to focus our attention on the rightmost derivative, the partial derivative of the log of 1 minus the sigmoid function evaluated at minus w transpose x. Well, let's go ahead and turn that subtraction into a single fraction. By doing that, we can cancel out the 1 and the minus 1, and we're left with the partial derivative of the log of e to the minus w transpose x divided by 1 plus e to the minus w transpose x. We're going to use the chain rule of the derivative again. In this case, what happens is that you get the log prime times the whatever's inside of the log prime as well. Now we know that the derivative of the log is 1 over whatever is the stuff that is the argument of the log. And in this case, we have the derivative of a quotient. So we're going to use the quotient rule of derivatives. What is that? Well, it's the numerator prime times the denominator minus the numerator times the denominator prime divided by the denominator squared. Now we know that there are other ways to solve this problem, but I'm going through the long and sure path. Now that we know what it's going to look like, let's go term by term. Well, we know that the derivative of the log is 1 over its argument. So the argument of the log, we elevate it to the power of minus 1. Next, we take the derivative of the numerator. That means e to the minus w transpose x. E to the whatever's derivative is the same e to the whatever. And then you have to multiply that by the derivative of minus w transpose x, which we get as minus x, since we already know, we talked about this before, that when you take the derivative with respect to w of w transpose m, you just get the constant m vector, which in our case is the blue x. Then the denominator, nothing happened to it on the first term, so we just copy that over straight. In the next term, the numerator gets copied over straight, and the denominator gets primed. In other words, we take its derivative. Derivative of 1 is 0. Derivative of e to the something is just e to the something, and then we have to multiply that because of the chain rule times the derivative of minus w transpose x. We get minus x for the same reason we saw above. And then the denominator is squared. We haven't changed that. Now we have this pretty unfriendly expression, but the nice thing about it is a lot of stuff is going to cancel out. For example, we know that that numerator is in the denominator squared. That term in the numerator is in the denominator squared, so we can cancel that out. In addition to that, the e to the minus w transpose x in the denominator is in both of the terms of the numerator, so we can cancel those out too, and that helps us simplify the expression. All right, now that we have this expression, which is not as simple as we'd like it to be, let's go ahead and factor out the minus sign in both of these. We're going to put it in front of the fraction. In addition, the x vector is also present in both terms, so we're going to factor it out and put it in front of the fraction. So we end up with this expression. Once we have that expression, we'll realize that e to the minus w transpose x is subtracted from the same term. So we can cancel those two guys out, and we're left with a much simpler expression here. We had already replaced the leftmost partial derivative with our resulting expression. Now let's go ahead and replace the rightmost derivative with our expression. And we'll notice that in both terms there is the x vector, which we're going to go ahead and factor out of both terms. Let's make some space for ourselves here. Well, the first thing that I want to do is to distribute the 1 and the label y over these two terms. So we break it up. The next thing I want to do is to put all the terms that have a y label in it together and the term that doesn't have a y label in it on the right side. This allows us to factor out the label on the left two terms, and it gets us an expression multiplying the y where the numerator equals the denominator. That simplifies the expression significantly, because then we get y super j, which is the label, minus 1 over 1 plus e to the minus w transpose x. In other words, g of x is on the right side. Hang in there, guys. We're almost there. First of all, let's make some space for ourselves. The summation, we know the rightmost term is the sigmoid, is the discriminant function, which is the sigmoid function evaluated at minus w transpose x. So we go ahead and replace that expression with g nu. Next, the minus front sign that's in front of the summation, we're going to bring it inside of the summation. So that leaves us the arithmetic average over all instances of g evaluated at each one of the instance feature vectors minus the label for each one of the features times the feature vector. Now remember, the feature vector in our case includes the bias. That's why we don't need two different formulas or two different equations. The bias is already integrated into our feature vector. That's the 1 at the top. And all the other scalars are the actual features for instance j. In addition, the label y is going to take on one of two possible values. It's going to be a 1 if the email instance is spam, and it's going to be a 0 if the instance is not spam, or rather good. The discriminant function is going to be our decision function. It's going to be a scalar between 0 and 1. Good news! We've finished deriving gradient descent for logistic regression. Step 1, we start off with an arbitrary w coefficient vector. Step 2, we evaluate the gradient at that first w. And we have an expression for the gradient. What is the gradient? It's 1 over n, summation from j equal 1 to n, of the new discriminant function evaluated at each feature vector minus each label, quantity times the feature vector. So now we have it, we can just plug it in. And every time you update, what you do is you take the previous step w and you subtract from it the learning rate times the gradient evaluated at the previous w point. And that's it. The next question is, will this converge to a unique global minimum? Or is there a risk of getting stuck at a local minimum? The only way to prove that this converges to a global minimum is to prove that this j function is convex, which is what we're going to do next. In order to prove that J is a convex function, we're going to need to take the second derivative and show that it is positive. We already have the first derivative. In other words, we already have the gradient. It happens to be a vector of length d, in other words, one element for each attribute. And we know that the gradient vector has each row equal to this expression that we found, 1 over n, the summation from j equal 1 to n of the g evaluated at x minus its label y of j multiplied by each one of the feature components. The top one is the bias, so it's just multiplied by 1, and all the other rows have the actual features. What we need now is the Hessian matrix, which is the second derivative of j. In this case, we're going to have to look at each one individually. So let's look at any arbitrary row I of this Hessian matrix and derive what it's going to look like. So this is the ith row of our Hessian matrix. Now we know from the linearity of derivatives that we can just take the partial derivative of whatever's inside of that summation. The x sub I, in other words, the ith feature of the jth instance, is a constant with respect to w, so we can just ignore that as a multiplicative constant. And we're subtracting the label y from g, so because of linearity, we could take the partial derivative of each individual one of those terms. We also know that y, the label, is a constant with respect to w, so that term goes to 0. That's nice. It simplifies stuff for us. And on the left, we simply have the partial of our discriminant function with respect to w. But we've done this before. Just for, sanity's sake, let's really walk through it very, very, very quickly. The leftmost term is minus 1 over the denominator squared. Because of the chain rule, we multiply that with the derivative of the denominator. 1 plus e to the whatever has a derivative 0 plus e to the whatever. And because of the chain rule, we still have to take the derivative of the whatever, in other words, the stuff squared. Therefore, we're going to be left with this expression. The average over all instances of the leftmost term, minus 1 over that denominator squared, times 0 plus e to the minus w transpose x times minus x. All of that has to be multiplied by the ith feature of the jth instance. And this is for row I of the Hessian matrix. This is what we have so far. What I'm going to do is I'm going to take that x feature vector transpose, and I'm going to write it out element by element. In other words, the bias term, and then the first feature for the jth instance, and the second feature for the jth instance, all the way to the d minus 1 feature for the jth instance. Now I'm going to distribute x sub I sup j into this vector, because it's just a vector multiplying a scalar. Now, I have the x sub I sup j into each one of the terms of that vector. Now, keep in mind, this was just looking at row I of this Hessian matrix. Let's look at all of the rows of the Hessian matrix together. Now, remember where we were a few slides back. We knew that we needed the Hessian matrix, which was the derivative of the gradient. And we said, let's just look at the ith row of this Hessian matrix, which we did. Now, we're going to replace each one of these rows with our findings. In each case, we have 1 over n summation from j equal 1 to n times of a scalar times a vector. And in each case, the vector is equal to the feature vector transpose times the scalar of the of the ith row, x sub I feature of the jth instance. This is what we have so far. So this is what we have for the Hessian matrix. Now keep in mind that that fraction, e to the minus w transpose x divided by 1 plus e to the minus w transpose x quantity squared, is a scalar, and it's the same scalar for each one of these vectors for each one of the rows. What does that tell us? It tells us that we can actually factor out that scalar from this matrix. And we end up with 1 over n summation j equal 1 to n of that scalar times this matrix with each one of the rows which we derived independently before. But notice that that matrix, what characteristic it is. This matrix is simply the feature vector multiplied by its own transpose. In other words, that matrix is equal to x for instance j times x for instance j transpose. This allows us to simplify things significantly. All right, so now we have an expression for the Hessian matrix. We just need to show that this is positive definite. Well, for each one of these j equal 1 to n terms, this denominator is something 1 plus something non-negative quantity squared. That's always going to be positive. So that term is positive in the denominator. The numerator is e to the something, so that's going to be non-negative also. So far we're in very good hands. The only thing that's left is we need to show that this matrix is always positive definite. And then we're done. Super quick crash course in linear algebra reminder. A matrix M is positive semi-definite if for all vector A of suitable size, so you can make this multiplication, then A transpose MA is non-negative. Let's try it for our matrix. Consider any arbitrary vector A of suitable size. Well, then A transpose, and here's our matrix, X transpose, times A. Let's look at the dimensions of the individual parts. A transpose has to be 1 by D. X is D by 1. X transpose is 1 by D. And A is D by 1. That means that the left two components multiplied together give you a 1 by 1 scalar. The same thing could be said to the right two components multiplied together give you a 1 by 1 scalar. Well, if the left two terms product is a scalar is equal to its own transpose. So I could replace A transpose X with A transpose X quantity transpose. That's perfectly allowed in scalars. That means that I have X transpose A times X transpose A, a scalar times a scalar. As a matter of fact, a scalar times itself, I get a scalar squared. And I know that any scalar squared is going to be non-negative, and this is going to be true for all A of suitable size. That means that X times X transpose is positive semi-definite. Guys, we are so close. We just need to show that this is a positive definite matrix. We've already shown that this matrix is always positive semi-definite for each of the n instances j equal 1 to n. Since each of the x transpose is multiplied by a non-negative scalar, that fraction on the left-hand side, then each one of them is positive, each one of the components is positive semi-definite. Therefore, j is a convex function. If we can just show that in addition to being positive semi-definite, that Hessian is full rank, then we will have concluded that j is in fact positive definite and therefore strictly convex, which is what we want. Here's another crash course reminder in algebra and probability. Well, if a positive semi-definite matrix like ours, M, is full rank, then it is positive definite. If you don't remember why this is, let's think about it. We know that if our matrix is positive semi-definite, then A transpose MA is greater or equal to 0. But if in addition M is full rank, then we know from linear algebra that A transpose MA is identically equal to 0 if and only if A vector is identically equal to the 0 vector. So if M is positive semi-definite and it is full rank, it must be positive definite. All right, what's that got to do with ours? We know that each one of these matrices that are being added are positive semi-definite. Now, let's assume that the features of different instances are independent from each other. In other words, for all of our training data, assume that the features of one email are independent from the features of a different training email. So the number of, for example, exclamation points that you get in email 1 are different than the number of exclamation points that you get in email 2. Not different, independent from them. Well, the other thing we're going to need to assume is that features have finite variances and means. What does that mean? That means that no email has, an infinite number of exclamation points or an infinite number of capitalized words. In other words, we're saying that the feature vectors are well behaved. Their averages are finite and their variances are also finite. Well, the central limit theorem tells us that when you average many independent, well-behaved random variables, then the behavior of the average begins to approach Gaussian as n, the number of instances, gets very, very large. Finally, a matrix of Gaussian random variables is full rank. Now we know that in order to have a good machine learning training algorithm, we want a large n, in other words, a large number of training instances. Therefore, for that case, we can assume that J is positive, that the Hessian of J is positive definite. We did it. We just needed to show that this Hessian matrix is positive definite. And we did show it. That means that J is a strictly convex function. And why did we care? Because if it's strictly convex, the gradient descent algorithm we described earlier for logistic regression will converge, and it will converge to the global minimum. So in this video, what we've talked about is logistic regression. We talked about why the sigmoid function is the right choice and the new cost function based on it. We talked about the new decision boundary. We proved that the new cost function is convex, and we derived the new gradient descent algorithm. I hope you can join us for our next lecture. Here at the Masters in Telecommunications program, we strongly believe that the best student experience involves hands-on labs and projects to equip our graduates to excel in the workplace. One of the things that attracts students to our program is that we are very industry focused. We keep a constant tab on the skills that hiring agents want, and we make sure that we offer courses and labs that provide these skills.